Welcome to Intelligent Dynamics Canada. My name is Dr. Baruch Pletner. I'm the President and Chief Operating Officer. And today we're going to talk to you about our new product platform for the detection and classification of vibration. So if you follow with me to our presentation screen, we will see our first our title slide, and that is the vibration detection classification using patented Intellivibe technology by Intelligent Dynamics Canada. Today we will talk about the Intellivibe piezoceramic packaging technology. We'll talk about vibration detection classification and specifically about the potential applications and markets. We will review the performance highlights of our products. We will talk about the state of development of our products. We will then review the technical approach and go into a proof of concept demonstration and discussion. Let us talk about our patented Intellivibe transducer packaging technology. This is the only existing technology that allows for embedding of piezoceramic transducers such as PZT, lead zirconium titanate, into standard printed circuit boards using fully automated techniques. So PZT, lead zirconium titanate, is a very common engineering material. It is used and has been used for decades in many applications for generating and sensing vibrations, for example, in sonar. What we have done is we have developed a technique for embedding this material into standard printed circuit boards, making it extremely mechanically and electrically robust. Let's talk a little bit about vibration detection and classification. There certainly are a large number of applications, and we'll cover a few of them here. The first one talks about detecting and classifying faulty operation in unmanned industrial equipment such as generators, pumps, etc., in order to avoid costly failures and unscheduled maintenance. So we all operate rotating equipment on a daily basis by driving our cars, or if we have pleasure boats or any other type of equipment of that nature. When that happens, we are the operator, so we know how that equipment should vibrate. We know how it should sound. We know how it should feel. And if we get into our vehicle in the morning and it's not sounding right, it's not feeling right, we will go through a number of operations, such as looking at our dashboard and seeing if there's any lights there, or maybe turning the engine off and on again to see if, in fact, there is something potentially wrong with our vehicle. And that just makes sense. However, there are many pieces of equipment of the same nature, such as diesel generators for backup power or for power in remote locations, that are expected to operate for many weeks and months without any human operator being on site and constantly monitoring that equipment. There is also a very important aspect of ensuring that the equipment is always operating at peak efficiency, not producing any unnecessary gas and or sound emissions. And that is something that is valuable for the planet, is valuable in terms of occupational health and safety, but is also valuable in terms of reduced fuel costs and reduced wear and tear on the equipment itself. Driving on roads outside of prescribed hours, there are many installations that are of sensitive nature, such as radar installations and power installations, and they have access roads that allow people to go there and service those installations. However, those roads should not be driven on during those hours that they should not be driven on, and if somebody attempts to drive on that road outside of those authorized hours, that may be something that somebody would want to know about. Sensors such as ours, or sensing systems such as ours, would be able to differentiate a vehicle traveling on that road from the normal vibratory and acoustic environment and alert the authorities to that event. Let us review some of the performance highlights. First one is the detection classification of subtle changes in vibratory and acoustic amplitudes and spectra as compared to a learned baseline that can always be relearned. The learned baseline and the ability to relearn the baseline are two very important characteristics of our product platform. The reason for that is that if you have a subtle vibration sensor that can sense minute changes in vibrations, that sensor will normally pick up the normal vibratory and acoustic signature from the environment, which is always present. And so the idea is then to be able to detect changes from that baseline when things occur that should not be normally occurring. The relearning piece is also very important because the normal is not static. So for example, with rotary equipment, the sound and vibration signature of a diesel generator may be quite different from, let's say, negative 30 degrees Celsius to positive 30 degrees Celsius. And both of these conditions exist, for example, in the oil fields of Alberta. So it may be necessary to relearn the normal baseline depending on, for example, the season, the time of year, and so on. In other situations, there could be just a different normal level of sound based on wind whistling through leaves in the summer, but since there are no leaves in the winter, there could be a different auditory and vibratory situation in other pieces, in other applications, such as, for example, monitoring restricted access roads and so on. So our system will have the ability to learn and then relearn upon command what is normal and then differentiate any departures from that normal. The system will communicate with the user via a full wireless suite of communications, including cellular, and we will demonstrate that today. Cellular short message system, satellite, GPRS in case of data, and we will talk about that later. And in some cases, we will offer Wi-Fi connectivity as well, depending on the user's preferences. Full recording of fault events with internal storage and upload capabilities. So especially in case of rotating equipment monitoring and those types of applications, it can be very important to learn what exactly happened when that fault was detected. How different was the vibratory signature then at that point from what is considered normal? And this type of analysis can be extended further by the user or by our company to really help understand what happened there. In order to do that, our system will record the last few seconds of operation when fault is detected, and this data can then be either stored on an internal storage and or uploaded to a cloud or a server that is in a remote location for further analysis and investigation. Moving right along, let us talk a little bit about the proof of concept demonstration, what we're going to see here next. So what we will see is a stainless steel beam equipped with 8 standard micro S1 Intellivibe sensors, making this beam into a piezoelectric bimorph transducer. We also have a number of simulated excitation or vibration environments, and those include a shaker, which is really just a speaker and an audio amplifier. We will demonstrate also the monitoring and fault detection block, which is executed in LabVIEW, and the analysis block as well. There will be normal operations which will be indicated by green virtual LEDs on a computer screen, and the fault operation will be indicated by those green LEDs becoming red, the termination of execution, and a short message sent to the registered users, in this case myself, a mobile phone.